All right, so yesterday we ended talking about designating R or S for stereocenters, and I gave you guys a bunch of rules, and we talked about that left-handed turn being an S as long as your lowest priority is pointed backwards, and then R would be if you're doing a right-hand turn and your lowest priority is pointed backwards. So we went through a few examples of these with tiebreaker situations, but I wanted to give you guys another challenge example. Okay, so let's say I've got this group over here. And a chlorine. Where's our stereocenter going to be? Central carbon. I agree. That is a stereocenter. It's got 4 different attached substituents. What's going to be highest priority? Ooh. Heaviest atom? Chlorine. Next heaviest? Fluorine. Next heaviest? Oxygen. And then carbon must be last. All right, so I'm going to go ahead and I'm going to connect all of these. But we're running into a problem. Our lowest priority isn't sticking out of the page or going into the page. So we're a little bit stuck at this point. But I'll show you guys a simple trick you can use. And I'll write this down. The problem is the lowest priority is in plane. What I like to do as a solution is imagine looking down this bond. So look down, lowest priority bond. And draw the front half of your Newman. All right, so I'll give you guys a minute to do that, but then I want you to talk with your neighbor and determine whether or not that's an R or an S if you look down that lowest priority bond. You guys are very quiet. Does that mean you got it or you're not understanding? It's hard to tell for me sometimes. Both. Thumbs up if you think you got it. All right, so I'll show you guys what I would do for my Newman, right? We're only doing the front half, so it's going to look like a triangle. What's sticking straight up? Fluorine. The fluorine, right? So the fluorine must be sticking straight up. What must be to the lower right? Chlorine, right? Because it's a dash going into the board, when you swing it around, it's going to be going to your right. The OH, that alcohol, is coming out, so when you swing it around, it's going to be going to your left. Okay, so we've got this front half of our Newman projection. We already know the priorities of each of these, so I'd say, all right, chlorine is 1, fluorine is 2, oxygen's 3. We're turning it to the left, so will this stereocenter be an R or an S? S. Yeah, if we wanted to do a full Newman projection, which is what you're asking, you could additionally have that back carbon shown, but the back carbon doesn't impact the stereochemistry at all. So I don't even bother showing it just because it confuses me. I just leave it as the front carbon only. Yeah. But oftentimes you may run into this situation where your lowest priority isn't a dash or wedge, and it does require you looking down that lowest priority bond and drawing the front half of the Newman. Does that make sense? All right, let's try another one. We're going to mix it up. All right, for this one, I want you to actually draw a compound from a name. Yep. So draw 1R, 2S, 1 bromo, 2 chloro, cyclohexane. You can draw it as a chair if you want, but I would recommend starting with the 2D top-down view and then maybe convert that to a chair later. I didn't say sister trans for this one. I just gave you R or S. What I recommend doing, I'll show you guys how I handle this, is I ignore stereochemistry at first. And I know the bromine's coming off position 1, so I'll just put that off the top. And I'm not going to show it as a dash or a wedge yet, just a straight line. And then off of position 2, I'm going to put a chlorine. As elegant as this sounds, I do guessing and checking. So for example, with bromine, I'm going to say, all right, I'm just going to arbitrarily pick a wedge. I'm going to leave the chlorine as a straight line because right now we're not focusing on that. Is this stereocenter where the bromine's coming off of an R or an S? Okay, highest priority we know would be the bromine, that's heaviest. And then if we look over here and over here, it's a carbon-carbon tie, but which one will be higher? The one with the chlorine. So I'm going to say 1, 2, and then over here, this must be 3. So if we go around like this, I'm turning it to the right. So that looks like an R to me because that assumed hydrogen has to be a dash, right? So I'd say this is good. We're in the correct confirmation. I just got lucky drawing this as an R. All right, let's do the same thing with the chlorine. Okay, this time, just for fun, I'm going to make the chlorine a dash. Then what I want to do is say, all right, this stereocenter, I'm going to draw it as green. We want to assign priorities again. So what will be the highest priority for that green stereocenter? The chlorine. Okay, so I would go ahead and I'd say, all right, this is priority 1. Then we go over here, and we've got a carbon-carbon tie. Yeah, the one with the bromine's got to be number 2. And then over here, this must be position 3. So if I go ahead and do that, it looks like I'm twisting it to the left, but the lowest priority is coming forward. So what would that stereocenter be in green? It would be an R. Do we want it to be an R? No. So how should I fix this? Make it a wedge. That's why I like guessing and checking, is it's pretty easy to convert from an incorrect dash to the correct wedge. So I'll just go ahead and draw it like that. So now this looks like the correct molecule. It's as simple as that. What I always do is I draw my parent chain or my backbone, draw my substituents in as a straight line, pick one that I know is a stereocenter, try it as a wedge, see if it matches. If it's not, I flip it. Make sense? You guys want another challenge one? All right. This is a 2-part challenge question. So part 1 is identify stereocenters. Part 2 is assign as R or S to any stereocenters that you find. Number 3 is name it. And number 4 is determine if it is chiral. So there's a lot of stuff going on here. Who thinks they've got it? A few people? Let's try to go through 1, 2, and 3 together. Number 4, I think, is a little tricky. All right, so number 1, let's identify stereocenters. How many of you think there's only one stereocenter? How many of you think there's 2? That's good. All right, so we've got one stereocenter right here. What's the highest priority for that red stereocenter? Chlorine. All right, between the left carbon and the right carbon, which one's higher priority? Right carbon, okay. So I'll say 2 over here. That means this one must be 3. So is that going to be R or S? R, right? It's twisting to the right. The lowest priority hydrogen is an assumed dash, which means we follow the normal rules. We're not flipping anything. All right? The next one, I'm going to label with green. We know is going to be really similar. It's going to have a 1 here, a 2 on that carbon, and then a 3 on that carbon. So again, this one's twisting right, but is it going to be R? It's going to be S because our lowest priority assumed hydrogen is coming towards us, so we want to flip it. So this is going to be an R and S stereocenter. All right, now what we want to do is name it. All right, so I'm going to redraw this really quickly down here. So what do you guys think we should name this? So without nomenclature, or without using R or S, we can put the parent in, and this would be 2,3-dichlorobutane. But what should our prefix be to designate the R and the S?
2R, 3S.
Okay, let's try this. We could say 2R, comma, 3S. That designates the stereochemistry, and then dash 2,3-dichlorobutane. All right, so that's assuming that I'm numbering going this way, right? What if I numbered the opposite way? So let's say I draw the same molecule over here in blue. And then I go 1, 2, 3, 4. I could number it that way, right? We've got the substituents still coming off of 2 and 3, but what would this be called? 2s3r. So 2s3r, 2,3-dichlorobutane. Which one's right? They're both right. This gets tricky. Which leads us into the next question. Determine if this molecule is chiral. How many of you think it's chiral? How many of you aren't sure? How many of you are just waiting for me to tell you? All right. So let's go back to our super duper basic rules, right? How do we determine if a molecule is chiral?
Make a model.
Make a model and see if the mirror image is superimposable, right? Do I have somebody who wants to hold up a model? Dylan again? All right, so I'll let you go over there and hold that. So you guys see how this is a wedge and this is a dash right there? All right, I'm going to do the mirror image one. Do we agree that's a mirror image? The question is, are these superimposable on one another? So we can spin this around. I'm going to grab this, grab this. I can lay it on itself atom for atom. So that means that this can't be chiral, right? So let's make a note of that. This compound is not chiral because it is superimposable on its mirror image. At which point a student will say this to me, but Jeff, there are stereocenters. Right? People get really hung up on the idea of stereocenters always being involved in chirality, right? We just saw an example, though, where stereocenters aren't involved in chirality. So what do you think's going on here? I'll give you a hint. It has to do with the trick I showed you with the pod. Symmetry, right? Okay. So I would say yes, but there is an internal plane of symmetry. So I'll show you guys kind of what I mean by this with the internal plane of symmetry, and I'll redraw the molecule just to make it clear. What I'm going to do is I'm going to imagine rotating this bond. We know sigma bonds can rotate freely in space from Newman projections. All right, if I do that, this chlorine is still a wedge, but what happens to the other chlorine coming off right here? Will it be a dash anymore? No, it'll flip to a wedge. This still has that same RS stereochemistry, right? We haven't changed the stereochemistry at all. But if you notice, this now has a plane of symmetry. This is a unique special case of organic compounds known as Miso compounds. So let's make a note of what a Miso compound is. A Miso compound is a compound that contains stereocenters but is achiral due to an internal plane of symmetry. The important thing to remember with Miso compounds is you may have to rotate sigma bonds in order to check for internal planes of symmetry. A lot of people look at that molecule on the top left and they say, well, there's no plane of symmetry because it's hard to see in that specific conformation. So you may have to do some conformational analysis to spot an internal plane of symmetry. Does that make sense? Yeah, it's tricky sometimes. And one thing I will say is these are some of my favorite trick questions for exams and quizzes. So make sure you understand Miso compounds because they may be thrown in on an exam. All right, so now the question is, how can we determine if a molecule is chiral or not? It's easy to see on paper, but we can't physically see molecules in real life. So we've got to come up with a technique in lab that allows us to determine chirality. So let's go ahead and take a look at this next section. And the first thing I wanted to show you guys was the schematic for a piece of lab equipment known as a polarimeter. And a polarimeter is pretty common in labs. What it does is it takes a special lamp, usually it's a sodium lamp. So they get those neon lights like you see on the streets. You guys know those kind of orange ones. Those are sodium lamps. And they shine that through a special piece of glassware that will actually plane polarize light. So light, you know, has a wave-like nature. What it will do is only allow waves that are going in a certain direction through. It's the same thing with polarized sunglasses. I'm sure a lot of you have polarized sunglasses. So really, it will only let one direction of light through. What that plane polarized light will do is then go through your sample. Your sample is held in a big chamber. That light goes through your sample, and that plane polarized light might be going like this when it's going in, but as it comes out, it may be going out at a different angle. So what's essentially happening is that plane polarized light is getting twisted as it goes through your sample, and that's how we can determine whether or not a molecule is chiral. So chiral molecules will rotate plane polarized light. It's kind of a unique phenomenon. So I'll show you guys just a really easy, simple example. And let's go back to one of our examples from yesterday, where we have a bromine sticking up here, a chlorine sticking out over here, we've got a fluorine, and we've got a hydrogen. Is this chiral? I'd say so. It's got a stereocenter and no internal plane of symmetry, so I'd say it's chiral. And if we draw its mirror image, we could also double check. So I'll draw its mirror image over here. So when we look at this, the one on the left, is that an R or an S stereocenter for that carbon?
That one's going to be on the right.
Yep, we're going to turn right. Hydrogen's the lowest priority. It's sticking back. So this will be our R. And then over here, what will the one on the right be? It must be 1, 2, 3. We're going left now, and our lowest priority is a dash. So that must be an S. And so let's say I have a pure sample of this compound on the left, and I shine plain polarized light through it. It might twist light a certain direction, maybe 20 degrees one direction. What do you think the one on the right might do? Yeah, negative 20, because they're mirror images of one another, right? So the one on the right will be a negative 20 twist when it pops out the other end of your sample. So let's make a note of this unique situation. These are referred to as enantiomers. Ugh. They are non-superimposable mirror images. So it's kind of neat. One enantiomer will twist light one direction, the other will go the opposite direction. There's no good way of predicting which direction the light will go, but you know the opposite will always be true for the other enantiomer. So let's get into the math and some of the nitty-gritty stuff. And I promise the math is pretty simple here. And this is referred to as optical rotation. All right, with optical rotation, what we have is alpha in brackets. And then we have some number in the top right-hand corner. It's usually 20. And then usually a symbol down here. And I'll show you guys what this means, but let me finish writing out the equation. It's alpha over C times L. And this is equal to your observed rotation divided by the concentration of your sample. And the concentration is always in grams per milliliter for optical rotation, not in molarity. And then the path length and the path length in this case is actually going to be in decimeters. I remember talking with my Chem 110 class last spring, and they were asking me, when does deci ever get used as a prefix, because they had never seen it. And I actually thought about it long and hard, and I was like, well, the only time I've seen deci used as a prefix is with optical rotation. It's pretty much the only time you see it. So what is a decimeter? It's a tenth of a meter, right? Also known as 10 centimeters. So the sample length is measured usually in a 10 centimeter sample tube. That's really all it means. Kind of unusual notation though, but historically this is how it's done. So for example, this alpha tells you that observed rotation divided by the concentration in grams per milliliter times the path length in decimeters. So the units will normally be in degrees over grams per milliliter times decimeter, right? So it's very, very unusual units for that alpha number. This 20 up here indicates the sample temperature. So it's the temperature in degrees Celsius. And then for D, this actually has to do with the type of lamp that you're using. So this is referred to as a D line from a sodium lamp. So how many of you guys remember from Gen Chem looking at spectral lines? Right, this is a unique line that's only observed in sodium, so it's kind of standardized that way. So there's a lot going on here. There's weird units involved, but we're not going to do a heck of a lot with math. There is one tricky sapling problem. I would recommend using a fair amount of scratch paper, and if you want to bring it to the review session tomorrow, we can actually go over it in person. All right, so let's take a look at some hypothetical situations. So what happens if we have a 50-50 mixture of enantiomers? Do you think the plane polarized light will rotate? If so, in which direction and by how much? I wouldn't think about this too hard. So let's go up and look at the enantiomers I gave you before. Yeah, let's say I've got an equal portion of the R and the S. One's going to rotate to the left, the other one's going to rotate to the right. When you add those together, they just cancel out and you get no observed rotation. So if we have a 50-50 mixture of enantiomers, the optical rotation of each will cancel out. And you will observe no rotation. This is a really unique situation called a racemic mixture. And that's where you have an equal mixture of enantiomers. Does that make sense? That canceling out? It's a little bit abstract. All right, so let's think about this another way. What happens if you have an unequal mixture of enantiomers? So what do you guys think? Do you think the number is going to get larger or smaller or cancel out altogether? Yeah, it depends on which one you have. Will the number get larger, do you think? Not really. So some of it will cancel out and it will lower that observed rotation a little bit. So not all of your sample will cancel out. Therefore, you will observe the excess amount of one of your enantiomers. Does that make sense? All right, so let's take a look at what we can do with that measurement. And this is referred to as enantiomeric excess. This is also sometimes shown as EE%. And I'll show you guys how to do the math for this. So you can calculate your percent enantiomeric excess by taking your observed rotation for your mixture and divide that by the observed rotation for a pure sample. everything needs to be held constant, meaning the concentration needs to be held constant, the path length needs to be held constant. But what we are going to do is compare those observed rotations, right? And then last but not least, we're going to multiply this by 100. Does that make sense? Pretty simple math, doesn't require any calculus or fancy stuff. All right, so let's think about this in context. So a chemist has a mix of enantiomers. The pure / wanted enantiomer has a optical rotation of alpha with 20 degrees and that sodium lamp that is equal to 10 positive 10. I'm not going to put all the units in for right now. All right, the sample or the mixture has an optical rotation of 5 degrees. What is the percent EE? So how do we go about solving this? Yep.
You could have 5 divided by 10 times 100.
Yep, simple as that. So 5 degrees divided by 10 degrees times 100. What should that be? 50%. Not too bad, right? That's one thing I really liked about organic chemistry when I took it, was there wasn't much math. All right, so let's kind of break this down. So what I like to do is I say 100 minus 50 equals 50. Okay? Really what we're measuring here is this is our excess that was observed. What do you think this remaining 50% must have been? It must have been our racemic mixture, right? Not observed, but still there. All right, now to get into the abstract. If we're thinking about our desired enantiomer, what percentage of our sample must be the desired enantiomer? 75? Why not 50? Yeah, exactly. So we know that this excess is our desired amount. We know it's 50%. And then 1/2 of 50 equals 25%. Therefore, when you combine both of these together, it's going to be 50% plus 25% equals 75% of your desired enantiomer. Does that make sense? So the percent EE isn't telling you how much of your sample is the correct enantiomer. You still have to back calculate how much was racemic in your sample and add that back in. Does that make sense? It's a kind of weird calculation.